Dr. Phys, Theoretical Physics, Convolution. We're going to look at our low-pass filter again and arrive at the general formula for convolution by studying this in detail. Here comes a square pulse. You have a charging phase during the time the pulse has its height here of 1 volt, and then after 1 second you then have your discharging phase. Now, by doing this, I am inspired by Richard Feynman's comment when he mentioned that Princeton experimentalists were getting results because they had built the instrument, they knew where everything was, they knew how everything worked. It was wonderful. So you know everything about this low-pass filter. We have done that by conventional methods, and we're going to see how that's a convolution and get real close to convolution. Now, it's also important to understand mathematical formalism too, and I want to encourage you to seek out, or when you take your math classes and other courses, to take that approach. Look at that. However, in this case, we're going to get down to the nitty-gritty with something that we've built ourselves and know everything about it. So let's go to our results from before. This is the charging phase, the charging function, and this is the discharging time over here, time t equals 1 and greater. So I'm going to look at this. I'm going to start with this function over here, and we're going to write down what we have, 1 minus e to the minus 1, and then e to the minus the quantity t minus 1. And I'm going to play around. I'm very close to the detail here, and so are you, because we have arrived at this from scratch, and it's a very, very simple idea: charging up and discharging. And this dotted line refers to if you were to have a long enough time, you would actually charge up to that maximum, but here the pulse does not give us enough time to reach that. So let's see what we have here. How about if we multiply things through? E to the minus that quantity t minus 1, there's one of them here, minus, and then here the e to the minus 1 multiplies the e to the plus 1 factor and cancels, and you simply have e to the minus t. And I then look at this and think, let's get that e to the minus t by itself. I think that would be nice, because if we do that, we have here an extra factor of e, because minus minus is a plus. That's a plus 1 in the exponent. It's just simply e. And over here, if I pull out the e to the minus t, I simply have a 1, and there's a minus sign there. So I look at that and say, maybe that's a result of some integral, where at the limits of integration here I had a 1 at the top and a 0 at the bottom. Now that's interesting. That would correspond to time t equals 0 and t equal the 1. Now I'm looking at this out here, and it's as if the integral only had to go from 0 to 1, and that kind of makes sense because there is nothing over here past 1. So this is 1, so that looks like it's promising. Let's pursue that. So we have then set this up here with an e to the u evaluated at 1 at the top limit and a 0 at the bottom, so you subtract, and that would have come from an integral. In fact, e to the u integrates to e to the u. And I see that 0 to 1, even though I'm beyond this, this t, I'm playing around out here. So I'm thinking this has something to do with that I only had to integrate from 0 to 1, so I'm thinking that perhaps f of u could be inserted in here, and that 1 could be t way out here and I would still get the same result. So we'll come back to that, but let's just see if this idea works inside this interval from 0 to 1. All right, and there I need to get this, 1 minus e to the minus t. I need to get that inside here. So let's do that. Let's check that. Let's check this integral from 0 to t, and here I integrate from 0 to t. I'm looking for here a t value inside that interval, so I'm going to integrate to the t, and when I do that I get here e to the minus t, and I get simply e to the u at the t, and then at the lower limit at the 0 I get the answer. That's exactly what I need to have, 1 minus e to the minus t. So that's very, very promising. And see, in that region, the f here function is a 1, and that suggests here that I insert the f of u function in there, so that in general, if I go from 0 to t, where I'm less than 1, surely this is 1, this f of u is 1 there, and I get this result. Now if I have t greater than 1, I want to get this result, and I do, because I only need to integrate from 0 to 1 because the f of u is dead when the time is greater than 1. So here, this is interesting, there's this u variable that comes in, and there's a t variable, but I integrate with that u variable. This is a convolution. We're looking at a convolution here. Now this equation here can be written by bringing the e to the minus t inside, since we're not integrating with respect to t, and we have this form for the convolution. It's the same equation as you have up here. And we say that we have a convolution here of the f of t function, which is simply that 1 square pulse over 1 second, and that is convoluted with the discharging function here, e to the minus t. Now what do I mean by that? I mean you replace t with u and put that there as the first factor. Then you take this function and do a t minus u for this variable. So instead of having the t by itself, you have the t minus u, and in general we're saying this: take the f function and put a u argument in there, variable, and then for the g put in t minus u. So this becomes e to the minus that quantity t minus u. And that is the formal definition of the convolution. Here's the notation. The convolution of f with g is written by this asterisk, and it means to do this. Now this is simply a way to re-express what we have done earlier. So this result here, our goal, our aim to get the convolution formula, this is it. Retrace those steps the other way or go forward. Just remember that this is simply giving us another way of understanding what we already understand completely, because as Feynman commented about those experimentalists, we have built that circuit up by hand, and we know this low-pass filter extremely well. We know this answer, and we're simply writing this solution in terms of another formalism, which is the convolution. But this is it right here. This is the convolution realized, and the other is a formalism.